Go.
Hello.
Yeah.
Welcome back from the summer break for our EVERSE webinar. We plan to return to a monthly webinar and training series. Our speaker today is Giacomo Peru. We will be recording it as you've seen and uploading it to YouTube. We ask that you keep your questions to the end. Giacomo, please go ahead.
Thank you, John. So welcome, everybody. I'm Giacomo Peru from the Software Sustainability Institute at EPCC, Edinburgh University's Supercomputing Center, presenting alongside Daniel Garijo from Universitat Politècnica de Madrid and Patrick Bos from the Netherlands eScience Center. This presentation demonstrates the reference framework developed by the EVERSE project. Okay. The framework serves two functions as both guide to internal activity and external statement. As internal guidance, it provides an overview of the considerations and perspectives around research software quality being taken by the EVERSE project. It supports practical tools including RSQKit and TechRadar by establishing theoretical foundations and ensuring consistency across project activities. As external statement, it communicates to those outside the project the approach being taken and connects various perspectives to software quality, excellence, and good practices, establishing EVERSE as a reference point for the broader research software community. The framework is structured.
Giacomo, you still have to share the presentation.
Oh, sorry. Yeah. Thought I was still sharing from before.
Yep.
Yeah. Okay, I'll show you my earlier slides, which are this one, and this one. Okay, great. Thanks, and sorry. So the framework is structured around four main pillars, plus four distinct views to address diverse community needs. The four main pillars cover technical aspects, fair software, open source software, and sustainability dimensions. The four distinct views provide different perspectives. The three tiers perspective examines software based on reach and complexity. The software lifecycle perspective considers development stages. The personas perspective addresses different user roles, and the science clusters perspective acknowledges domain-specific requirements. The framework accommodates diverse community needs and is adaptable to different software types. Requirements vary significantly between simple scripts and complex applications. The framework's principles acknowledge that a simple script should be treated differently than a complex multi-user software product, with all views potentially changing depending on the software type under consideration. Research software is commonly used to refer to software used and/or generated in a research context, including and not limited to scientific, non-scientific, commercial, academic, and non-academic research. The definition refers to objects to which the FAIR principles should apply. Software is an important component when it comes to reproducibility, where a different team needs to use the same research. Key distinctions separate research software from software in research. Research software is where quality directly impacts research outcomes and scientific reproducibility. Software in research refers to general-purpose tools, libraries, or infrastructure components that support research activities, but were not developed specifically for research purposes. The definition recognizes that software exists on a spectrum from research-specific to general-purpose tools. The reference framework focuses on software where quality directly impacts research outcomes and scientific reproducibility. establishing clear boundaries for framework application whilst acknowledging the spectrum nature of research software ecosystems. Research software quality is defined as the degree to which software supports reliable, efficient, maintainable, and trustworthy research. Quality encompasses multiple dimensions, including correctness, performance, maintainability, usability, robustness, and reproducibility. Quality research software enables researchers to trust, share, and build upon computational work, making science transparent and verifiable. Fair software principles represent a crucial subset of quality, ensuring software can be discovered, understood, and exercised by others whilst supporting long-term reproducibility and research integrity. A key aspect of software quality is reproducibility, the ability for others or your future self to run the software and obtain identical results using the same inputs and environment. This requires consistent and deterministic behavior, comprehensive version control and documentation, automated testing, environment management, and clear and accessible code. The EVERSE Reference Framework addresses quality through formal dimensions and indicators that address and improve these essential aspects of research software excellence. So, in EVERSE, we structured the discussion around research software quality with three main concepts arranged in clear hierarchical relationships. Research software quality dimensions represent common criteria relevant for assessing software quality at a conceptual level, such as documentation, performance, maintainability, and security. These provide the theoretical foundation for quality assessment. Research software quality indicators represent specific aspects of software that can be measured at a lower level of granularity, such as fairness metrics, test coverage percentages, documentation coverage statistics, and security vulnerability counts. These translate abstract dimensions into measurable characteristics. Research software quality tools are instruments that measure software quality indicators against specific criteria or alternatively help improve particular aspects. Examples include linters for code quality, OpenSSF scorecard for security assessment, and documentation generators for maintainability. The example flow demonstrates this hierarchy. The maintainability dimension as defined in the ISO IEC 25010, from now on I will just say ISO because it's a bit long, may be associated with an indicator checking whether continuous integration tests exist in a source code repository as defined by the OpenSSF community. An assessment tool like the OpenSSF scorecard implements the indicator by examining whether projects run tests before pull requests are merged into GitHub, whilst different quality assessment tools may check the same indicator against GitLab repositories. The EVERSE framework encompasses 12 main dimensions of research software quality derived from established standards and research software best practices. This consists of 9 technical dimensions based on the ISO IEC standards plus fairness, open source software, and sustainability dimensions that reflect the unique requirements of research software. The 9 technical dimensions are based on the ISO IEC standards, universal software quality characteristics applied to research contexts. These provide comprehensive coverage of technical aspects whilst being internationally recognized and standardized. The 9 FAIR represents findability, accessibility, interoperability, reusability adapted specifically for research software characteristics. These dimensions addresses software's executable nature, composite structure, continuous evolution, and the importance of source code access for the true reusability. Open source software encompasses practices that align with academic research purposes and enable verification, reproducibility, and community collaboration. These include source code availability, appropriate licensing, integration with open source ecosystems, and alignment with community practices. Sustainability addresses the capacity to continue being available, evolving, and meeting new needs over time with appropriate governance. This encompasses technical maintainability, community governance, funding model, and institutional support. These 11 dimensions reflect the unique requirements of research software, extending beyond traditional software engineering concerns to address the specific challenges and opportunities within research context. The framework adopts 9 top-level ISO IEC quality dimensions with 39 sub-characteristics providing comprehensive technical coverage. You can see the full list in the reference framework document itself, which should be linked in the Zoom chat. Note the examples of tools that measure dimension from the EVERSE Tech Radar. Compatibility represents the degree to which a product, system, or component can exchange information with other products, systems, or components and/or perform its required functions while sharing the same common environment and resources. Flexibility represents the degree to which a product can be adapted to changes in its requirements, context of use, or system environment. Functional suitability represents the degree to which a product provides functions that meet stated and implied needs under specified conditions. Interaction capability represents the degree to which a product can be interacted with by specified users to exchange information via user interfaces in various contexts. Maintainability represents effectiveness and efficiency for modification, improvement, corrections, and adaptation. Performance efficiency represents the degree to which a product performs its functions within specified time and throughput parameters using resources efficiently. Reliability represents consistent performance of specified functions under specified conditions for specified periods. Safety represents avoiding endangerment to life, health, property, or environment under defined conditions. Security represents defense against malicious attacks and information protections with appropriate access levels. Research software may place different emphasis on these dimensions compared to typical industry applications, often prioritizing functional correctness and performance over user interface aesthetics. The FAIR principles for research software adapt and extend the original FAIR principles for data to address the unique characteristics of software. Key considerations in applying FAIR to software include software's executable nature compared to static datasets, software's composite structure often involving multiple components and dependencies, the continuous evolution and versioning of software, and the importance of source code access for true reusability. The FAIR for research software principles aim to make research software findable, software and its associated metadata should be easy to find for both humans and machines through appropriate identifiers and rich metadata. Accessible software and metadata should be retrievable via standardized protocols with clear accessibility procedures. Interoperable software should be able to exchange data and work with other software via common formats and APIs following community standards. And reusable. Software should be well described and include clear usage licenses to enable reuse, modification, and integration into other software systems. Key recommendations for implementing FAIR for research software include using persistent and unique identifiers for software and its versions, providing rich metadata to describe the software functionality and context, using open standardized formats and protocols for data exchange, providing clear licensing and usage information for legal reuse, and following community standards and best practices established within specific domains. The FAIR for Research software principles provide aspirational guidelines that software creators and maintainers can work towards incrementally. Tools and practices continue to evolve to support FAIR software across different research domains, with the RESA Actionable FAIR for Research Software Task Force developing good enough guidelines to help make research software FAIR based on practical implementation experiences. Research software can be published with or without open access to source code. Open access to source code aligns better with academic research purposes than closed source software and supports FAIR for research software principles implementation. Research-driven benefits include method verification, where researchers can directly verify the methods used to produce results published in the paper, making scientific validation more transparent. Enhanced reproducibility becomes much easier when source code is available for examination and reuse. Cost-effective maintenance emerges since interested developers can easily contribute to new functionality or fix bugs, reducing maintenance burden on original developers. Ecosystem integration allows leveraging tools and support communities already available within the broader open source ecosystem. For most academic communities with limited resources, open source represents a beneficial choice from a software engineering perspective. Exceptions may be communities with very specific needs and ability to secure long-term funding to develop and support their own software, where the open source community may not offer sufficient benefits or have interest in contributing. Publishing software as open source is not completely free of cost, especially when adhering to common quality standards. Requirements include providing user support, interacting with potential contributors, dealing with licensing complexities, and maintaining adherence to quality standards. Sustainability dimension. Software sustainability can be defined as the capacity of a piece of software to continue to be available in the future on new platforms, meeting new needs. This means that it is easy to evolve and maintain, fulfills its intent over time, survives uncertainty, and support relevant concerns, including political, economical, social, technical, legal, and environmental factors. Software sustainability encompasses multiple interconnected aspects that ensure research software remains viable and remains viable and valuable over time. Technical maintainability ensures software is easy to evolve and maintain over time through good coding practices, documentation, and architectural decisions. Community governance establishes clear processes for decision-making and contribution, ensuring sustainable community participation and leadership succession. Funding models provide sustainable resource allocation for ongoing development, including both direct funding and in-kind contributions from institutions and communities. Institutional support ensures recognition and support from host organizations, providing stability and legitimacy for software projects. The sustainability requirements may vary significantly depending on the software tier. Analysis code may need minimal long-term planning and can often conclude its life cycle after serving its immediate research purpose. Prototype tools require more substantial planning for potential community adoption and ongoing maintenance. Research software infrastructure requires comprehensive governance and funding strategies due to its critical role supporting multiple research communities. Sustainability practices should be used together, supported by governance procedures. Extensive information on governance goes beyond tooling, and different combinations of practices may be useful depending on the software's audience as defined by the different views. All 12 dimensions work together in an interconnected framework where no single dimension operates in isolation. The relationship between dimensions creates synergies where improvement in one area often supports improvements in others. Context-dependent emphasis means different contexts require different prioritization of quality dimensions. Software tiers influence emphasis. Different tiers emphasize different quality aspects based on their reach and complexity. Life cycle stages affect priorities. Quality priorities change as software matures from initial development through maintenance and evolution phases. User personas create varying focus. Different roles prioritize different quality dimensions based on their responsibilities and expertise. Science domains establish practices, disciplinary practices influence quality, understanding, and implementation approaches. This multidimensional approach provides the foundation for the 4 views that help users navigate quality considerations appropriate to their specific situation. The views act as lenses through which the core quality dimensions can be interpreted and prioritized based on actual context rather than abstract requirements. Rather than rigid requirements, the framework offers flexible guidance that can be interpreted and prioritized based on actual software use and community needs. This flexibility ensures the framework remains applicable across the diverse landscape of research software whilst maintaining coherent underlying principles. The integration of dimensions creates a comprehensive approach that addresses both technical excellence and research-specific requirements. So, the 4 views. Research software quality cannot be assessed through a single universal approach. Different stakeholders, contexts, and purposes require tailored perspectives on what constitutes quality and excellence in research software. To address this diversity, the framework provides 4 complementary views that help users navigate and apply quality considerations appropriate to their specific situation. The 4 views include 3 tiers view, recognizing the different types of research software. The software lifecycle view acknowledges that quality considerations vary depending on where software sits in its development and maintenance lifecycle. Persona's view understands that different roles in the research ecosystem have varying priorities and responsibilities regarding software quality. And the science cluster's view recognizes that different research domains and communities have established practices and standards of their own. The three-tier model provides a framework for understanding the diverse landscape of software in research through an abundance versus rich relationship. This model distinguishes three tiers of research software, each with distinct purposes, stakeholders, and quality requirements. Analysis code demonstrates high abundance and low reach characteristics. This tier includes the most common type of research software, but typically has limited reach beyond immediate creators. These represent personal use software with small scope. Prototype tools exhibit medium abundance and medium reach. This tier bridges individual research and broader community use, designed to answer multiple research questions and typically developed by teams rather than individuals. Research infrastructure shows low abundance and high reach. This tier represents broadly applicable research software with the widest reach, often maintained by large distributed development teams and serving as foundational tools for many researchers. This three-tier model, originated from the Australian Research Data Commons as part of their National Agenda for Research Software and has gained international recognition. I'll have to skip a few slides as well. Time. The software lifecycle view. There is a close relationship between the software lifecycle and the three-tier model. Depending on the tier of software, the length of the lifecycle and number of iterations through the lifecycle may vary significantly, reflecting different development complexity and community engagement levels. Lifecycle patterns by tier show distinct characteristics. Analysis code follows streamlined lifecycle directly driven by specific research questions, requiring minimal planning and software engineering effort and limited documentation and testing. Prototype tools exhibit more complex lifecycle patterns with closer connections between research and software development cycles, needing extensive development planning to ensure alignment between software and research goals. Research infrastructure operates with software and research cycles no longer directly connected, requiring large distributed teams with advanced software engineering techniques for sustainable development and maintenance. The framework recognizes that research software life cycles vary based on developer groups and their intentions. The aim is to illustrate how different development contexts create different life cycle requirements and quality priorities. As part of understanding research software lifecycle patterns, it becomes important to achieve common understanding of processes in research software engineering to assess infrastructure needs and quality requirements appropriately for different software types and development contexts. It might be good to have a link to the RSQ kit in the chat. So, the research software lifecycle developed for the Research Software Quality Kit provides an alternative circular model emphasizing the connection between research and software aspects through 6 integrated stages. The circular model includes planning, covering research context and requirements analysis, development encompassing design and implementation phases, release involving deployment and publication activities, maintenance addressing evolution and sustainability concerns, documentation ensuring quality assurance and knowledge sharing, and community enabling feedback and collaboration processes. Key highlights of this model include the iterative nature of research software development, recognizing that development rarely follows linear progression, but involves multiple cycles of refinement and improvement. Decision points where quality considerations become critical are identified, helping developers understand when to invest in quality improvements. Integration points with research workflows ensure software development aligns with research objectives and timelines. Opportunities for tier progression are recognized, helping identify when software might evolve from personal use to broader community adoption. This model particularly emphasizes the interconnected nature of research and software development, unlike traditional software development models that may separate technical and user requirements. The research context remains central throughout all life cycle stages, ensuring software development serves the research objectives effectively. The RSQ Kit model provides practical guidance for navigating software best practices by connecting lifecycle stages to specific quality recommendations and tools, making the theoretical framework actionable for research software developers across different experience levels and institutional contexts. Persona's view. Research software quality considerations vary significantly depending on one's role in the research ecosystem. The persona's view recognizes that different stakeholders have distinct responsibilities, priorities, and levels of engagement with software quality practices. Core personas in research software include 5 primary personas identified within the research landscape. Researcher, who codes represents scientists and researchers who develop software as part of their research activities, ranging from simple analysis scripts to more complex tools, with primary focus often on functionality and getting research results. And this persona often hasn't had a formal software development training. Research software engineer encompasses professional software developers working in research contexts who bring software engineering expertise to research projects, typically prioritizing technical quality dimensions while understanding research-specific requirements. Principal investigator includes research leaders responsible for project oversight, funding, and strategic direction, with software quality interests often centering on sustainability, compliance, risk management, and ensuring software supports research objectives. Policymaker covers individuals involved in developing guidelines, standards, and policies for research software at institutional, national, or international levels, focusing on frameworks for assessment, recognition, and funding criteria. Trainer encompasses educators and training coordinators who teach software development skills to researchers, needing to understand quality practices across all levels and translate complex concepts into accessible learning materials. Different personas emphasize different aspects of the diverse quality framework. Technical dimension, C. RSCs typically leading on technical quality implementation, while researchers who code need guidance on achieving adequate technical quality without extensive software engineering background. FAIR principles are valued by all personas, but researchers and PI may focus more on discoverability and reusability, while RSCs implement the technical infrastructure to achieve fairness. Open source practices often see policymakers and PIs driving open source decisions at strategic levels, while RSCs and researchers who code handle implementation details like licensing and contribution workflows. Sustainability sees PIs and policymakers focusing on long-term planning and funding models, while RSCs and trainers work on technical and educational approaches to sustainability. Effective research software quality emerges from collaboration between personas rather than isolated individual efforts, with different combinations becoming more important as software progresses through tiers and requires more specialized expertise and community management. Okay, I can give the other slide. So role specialization and software tiers show clear relationships as research software progresses through the three-tier model. Analysis code is often developed by researchers who code working independently, with minimal role differentiation reflecting the personal nature of most analysis code development. Prototype tools may involve collaboration between researchers who code and RSCs, with PIs providing oversight and direction as software gains broader applicability and user base. Research software infrastructure typically requires teams with specialized roles, including dedicated RSCs, formal project management, policy oversight, and structured training programs to support diverse stakeholder needs. Effective collaboration patterns emerge from successful research software projects. Researchers who code and RSCs collaborate on balancing research needs with technical best practices, ensuring software serves research objectives whilst maintaining technical quality. PIs and policymakers align project goals with institutional and community standards, providing strategic direction and ensuring compliance with relevant policies. Trainers work across all personas to build capacity and share knowledge, helping different stakeholders understand quality practices relevant to their roles. RSCs often serve as bridges between technical implementation and research requirements, translating between different stakeholder perspectives and needs. The science cluster view. Domain-specific approaches recognize that different research domains and communities have established practices, standards, and cultural approaches that influence how software quality is understood and implemented. The science cluster view acknowledges these differences while maintaining overall framework coherence. EVERSE science clusters represent software use cases from 5 EOSC science clusters used in feedback loops between EVERSE and scientific communities. SSHOC contribute UDPipe, a multi-language textual analysis pipeline of tools that can operate locally or as a service, demonstrating humanities and social science software requirements. Escape provides ML-enabled data compression, reconstruction, and data analysis software built for open science, showing high-energy physics computational requirements. Life sciences research infrastructures offer secure and federated workflow orchestration for handling sensitive biological data performance for handling sensitive biological data across institutions. PANOSC enables heterogeneous computing and high-performance computing scaling for photon and neutron science applications. Henry Community provides EnFreeHub knowledge base and virtual research environment for environmental research infrastructure coordination. While software quality dimensions are meant to be general and cross-field, cluster-specific aspects exist due to technical and cultural differences. Technical differences arise from domain-specific computational requirements, data types, performance needs, and integration requirements with existing domain infrastructure. Cultural and work environment differences emerge from established practices, collaboration patterns, funding structures, and community expectations that vary significantly between research domains. These differences mean that the personas will be supplemented by other roles in some clusters, and that certain dimensions will be considered more relevant by some personas in certain clusters. The framework accommodates these differences whilst maintaining consistent underlying quality principles across all domains. Got time to go through this slide, yeah? Okay.
You got about 5 minutes left.
5 minutes left. I think I skipped this slide. Yeah. Okay. So before we conclude then, we've been discussing whether to introduce community as a additional quality dimension. Communities are often overlooked in traditional software quality frameworks, but for research software, a strong community can compensate for technical weaknesses. We already see community aspects implicit in our sustainability and open source dimensions. We are exploring 3 approaches for this. First, making community a full dimension with its own indicators and good practices. Second, explicitly integrating community aspects within existing dimensions. Third, treating it as a cross-cutting theme woven throughout the framework rather than a separate dimension. We are considering metrics like engagement and contributor activity, governance structures, communication effectiveness, and community health indicators from initiatives like CHAOSS. There's a clear relationship between community strength and software sustainability. Conclusions. So, in conclusion, the EVERSE framework provides a comprehensive approach to research software quality through 12 quality dimensions viewed from our perspectives, creating a multifaceted framework that serves diverse community needs. Key contributions include a structured approach where quality dimensions, indicators, and tools provide clear conceptual hierarchy for understanding and implementing software quality improvements. Flexible application through 4 views enable tailored quality approaches that can be adaptable to different software types, development stages, user roles, and research domains. Research-specific focus extends beyond traditional software engineering to address unique research software needs, including reproducibility, FAIR principles, and academic collaboration patterns. Community-driven development incorporates input from research communities across EVERSE's 5 science clusters, ensuring practical relevance and broad applicability. The framework's strength lies in its multifaceted approach, enabling it to serve the diverse needs of the European research software community while maintaining coherence in its underlying principles. The framework represents both theoretical grounding through established standards and practical guidance through concrete examples and tools, making it applicable across different levels of software engineering, expertise, and institutional context. The framework supports the development of practical tools within EVERSE, including the RSQ kit and the Tech Radar, whilst providing theoretical foundations. So thank you for listening. The current version is available on Zenodo. There should be a link in the chat. The recording of this webinar will be available soon. And yes, contact the EVERSE Reference Framework team if you have questions, and stay connected with EVERSE through the network webinar series, follow project updates and outputs, join discussion on research software quality. And we are happy to take some questions if you have any.
So if you have questions, you can either write them in the chat or you can also speak up. You should have all permissions to unmute yourself and just ask a question directly. Also, thank you, Giacomo, for the presentation.
Thank you for hosting me.
Yeah, thank you, Giacomo. I think it's a lot to take in one stand, right? So maybe while while we wait for questions, we can just discuss some of these aspects. But well, let's see what people think. If you, I also put in the chat a few other resources that are associated with the project, including the technology watch that includes tools associated with each of these dimensions, the pointer to the EVERSE training materials portal where we are linking training materials for each of the activities that are pointed from the RSQ kit that Giacomo mentioned, and also the list of indicators and dimensions that Giacomo mentioned during the presentation, right? So well, I hope that you also find those interesting. I see that we have a first question. Maybe Giacomo, you want to go ahead?
So maybe I read the question. John asks, how do I apply the EVERSE reference framework to my source code?
Oh, I can jump in on this one if you want.
Yes, please.
So one of the things that we are working, that I was about to put in the chat as well, is that we are developing the EVERSE research software quality pipelines. These take the form of a GitHub action that implement, using existing tools, all the indicators that we have in our list and will apply to your code. So this is in very, very early release. This is not official, so I'm sharing things that maybe I shouldn't at this stage. But in case you want to play around with it, we are working on this actively right now, right? And the idea is that you can configure which indicators your community is most interested in. We will be providing some default templates that select, well, if you are if you are dealing with infrastructure software, these are the indicators that we believe are relevant for you, but you can edit them if you think that some are not relevant for your community. And then you will be able to run these in your software using existing tools, because we are not redefining the tools. We are using a lot of tools that already exist for profiling code, for doing some static code analysis. Some are a little bit on fairness. Some check, like the OpenSSF card, right? There is already a tool that runs a series of tests that checks all those indicators. So yeah, I hope that answers the question.
Can I jump in here? So the reference framework itself, I wouldn't see as something that you apply straight away. It's it's a reference document where we've collected the approaches that we've taken in this research project around research software quality, and as we've seen at the beginning, serves the two needs of guiding the EVERSE activity and making a statement to the external world. You can read the document and check where your software falls in the various categories that we've listed there. Is it a prototype tool, your software? Is it a research infrastructure? What are you acting as a PI or as I don't know, a researcher or a research software engineer? But what Daniel was indicating is something that can be directly applied. And I would recommend looking at the RSQ kit for something practical that you can probably apply to your code. Do we plan to, I think that, Daniel, you've replied to these follow-up questions from John Shepherdson, right?
Yeah, I can elaborate a little bit if you want. So the first one, whether we have run the quality pipelines on its own repository, I think we have not done it so far because, again, it's very early work. But I think we should, and we will. As for the second one, do we plan to implement GitHub or GitLab badges? That's a good question. I'm usually a little not very enthusiastic about giving badges for everything. But I think this was discussed in the General Assembly meeting briefly. Sometimes badges, well, they are just something binary that it just states whether you have accomplished something or not. Many of the tools that run these tests give the badges, like the OpenSSF card, they will give you a small badge. And since this is so customizable, right? Because you can depends on which type of research software you're dealing with. It depends on the community. Maybe the different clusters can describe what is it a good enough badge for them. This is still under discussion. I'm not sure we are there yet to do the distinction in badges, but well, this is my personal point. So maybe some others have a different opinion so far.
So just added the dashboard with the detailed charts instead of a badge, maybe.
Yeah, as suggested.
Thanks for that.
Farouk, yeah.
Yeah, in fact, Farouk is in charge of creating this dashboard, right? And I hope that we are starting to see the early results of collecting all these indicators, and I hope that maybe in the next webinar we can show some actual information on how it is collecting stuff, right? Once it gets a little bit more stable.
Maybe I can ask a more general question. Since you had so much to discuss, you didn't really talk about how the reference framework is evolving, how much it's evolving and how it's evolving, Giacomo.
Yeah, it is evolving. This is the first. There was a previous version, but this we can consider this the first stable version of the reference framework. We plan to publish version 3 of the reference framework in early February 2026, just before the next General Assembly meeting. This will not be a major restructure because we are building on solid foundations at this point, but we'll finalize the approach on the community dimension. We incorporate learnings from the RSQ Kit, Tech Radar, and the other activities, other work packages of EVERSE. We will refine indicator based on adoption patterns. And yeah, more or less, this is what we will do in, and probably we will present it again in this webinar series. Daniel, you've got a raised hand.
Yeah, I wanted to clarify something that I think is also important in this context, that while the structure and the mechanism of the framework, I agree with you that it's stable, the list of indicators is far from being complete, right? We do have to include, so we did an analysis of over hundreds of indicators that are defined in the state of the art, but so far in the current implementations that we have that implement the framework, it's only a few dozens, right? So we are in the process of finding the tools that already exist that measure these indicators to make sure that all the quality dimensions have at least indicators that address them. Otherwise, if you have a quality dimensions with no indicators, that's not a very useful quality dimension, right?
Yes.
So those are the, so I just wanted to clarify that is still in flux. And the number of indicators will be varying probably until we do the final release of the model.
It is still in flux, and yes, we are moving towards a better, more coherent and more applicable framework, indeed.
We would have time for one last quick question if there's any.
And I'm about to be kicked out of the room where I am. But yes, we are still within the time of the hour.
Right. Otherwise, Giacomo said, get in touch if you have more questions with the people you've seen pointed out here, or with EVERSE directly. Of course, you know, stay in touch. We got the network, we got the newsletter, which I'm gonna post right now. We are on social media, have a look for us. And yes, thanks Eleonora for pointing it out. We are planning to do another webinar in a month's time. This is gonna be more training based, so it is to have something more topical and going to training, something more topical training. But you will be updated either by the newsletter, by the network mailing list. You can find all the information on the EVERSE webpage and on the Indico. This recording will also be made available on YouTube, on our dedicated EVERSE YouTube channel. I'll stop it right now.